Okay, now let's talk about how to compare more than two samples. And you remember that in the parametric approach, this is done by using ANOVA. For example, if you have only one factor, then you use a one-way ANOVA, right? The analog, the non-parametric way to do ANOVA is called Kruskal-Wallis test. And sometimes it's called ANOVA on ranks, although it's not precisely ANOVA on ranks. The algorithm is a little bit different. We will see it in a minute, but it's very close. Okay. So let me again use a simple data set where I have three groups, A, B, and C. Let's keep the same legend, right, about the tablets from three different companies, and we would like to find out if at least one is different in terms of how long they can work without recharging. So you can see that I have working time of these 30 tablets produced by three companies, and I would like to make analysis, right? So if I look at the distribution, if I look at the box plots, I can clearly see that indeed the tablets of company A have a shift again, right? So comparing to the tablets from the company B and C, right? So probably here we have no difference, but here we have a clear shift, right? But because we have some outliers, and you can clearly see, for example, this is average, this is median, this is average, this is median. So therefore, it's not a good idea to use a parametric approach here. If we do it anyway, so if we apply ANOVA, you can see that I just put these values as a vector y and g, all these values, right? Y will be the real values and g will be just AAA, BBB, CCC, the groups. Then you can see that in this case the p-value is pretty large, and we cannot reject null hypothesis about the equality of the means or equality of the distributions, right? Well, you can clearly see why here. So this is the cuckoo plot for residuals, and then you can see that although ANOVA is actually quite stable if you have minor deviation from normality, but in this case the deviation is not minor, right? It's pretty large deviation, so therefore it kind of hides effects, so ANOVA cannot see the effects, also the effect is there, right? Now let me show you how Kruskal-Wallis takes this, so how to use Kruskal-Wallis to make ANOVA. Again, you can see the step-by-step guide here, but I will show you all these steps in a minute just by using this example. So you will see all the calculations and so on. So step one, again, we need to merge all values and compute ranks, similarly to what we have done for Mann-Whitney test. In this case, I don't have place to merge all the values, so you can simply trust me that indeed all these ranks, so these are rings, right? Rings. All these rings are computed for all values together without splitting them into A, B, and C. We can quickly check it. If you look at these values, you can see this is the smallest value, and rank is equal to 6, right? And then you can see that, for example, this is the largest value, and then you can see rank is equal to 30, right? But the value which is mixed larger, so to speak, right? It's here. It's 15.9. You can see that there is no value larger than 15.9, but smaller than 18.9. So therefore, this rank 29 is here. Okay. So these ranks are computed for all values together without splitting them to A, B, and C. But then I split the ranks again. So now you can see a table with ranks. So the next step number 2, is to compute mean. 2 means actually, or 4 means in this case. First, I compute mean for every group. So this is mean rank for every group. You already see the shift, right, between A and the others. And then I compute the grand average, the total average rank, and this is 15.5. You can see it here. Okay. So now we need to compute distances again. Like in ANOVA, we compute distances and sum of squared distances, the same procedure here. First, we compute distances from the original ranks and the global mean, right? So for example, why it's minus 6.5? It's 9 minus 15.5. It will be minus 6.5. Why this one is 2.5? It's 18 minus 15.5. It's 2.5. So it's simply distances of all these ranks from the global mean. Okay. After that, we need to compute a sum of squared distances. So we simply take squares. So 6.5, for example, minus 6.5 squared will be 42.25. So we simply square every value, and then we can sum all these values up to get a sum of squared distances for the original ranks. So this is the sum of squared distances for the original ranks. Okay. Now the next is to find the explained part, right? So what if we don't have any noise? Then all these values should have the same rank, right? And this we just take an average here. It will be here. Average here is here. And average here is here, right? Now the same idea. Let's compute how far these expected ranks are from the average. So we simply compute distance between this and global average, this and global average, and this and global average, right? And then we fill this table with the distances instead. So these are the distances, right? So for example, why this one is minus 5.8? It's 9.7 minus 15.5. If you compute it, you will get minus 5.8, right? So the same idea, we compute a sum of squared distances, but now for the expected values. And first we square them and then take a sum. So this is a sum of squared distances. And this is the difference. In ANOVA, you remember, we also compute residuals and computed sum of squared residuals. Then we compute F value based on sum of squared residuals and the sum of squared explained values and so on. Here we will not do it. Here we will have a statistic based on these two sums. And this statistic is called H statistic. You can see it's n minus 1. It's a total number of values you have on all groups together. And then ratio between the explained sum of squares and the total sum of squares, right? And that's what we have, 6.5. So it's this divided to this, vice versa, this, the explained part, divided to this, and then times 29, because we have 30 samples, 30 values, 29 is n minus 1, right? So what to do with this statistic? This is again statistic based on ranks. We did some calculations and compute statistics which follow a theoretical distribution. Which one? Well, if null hypothesis is true and if sample is large enough, then it follows chi-square distribution, right? And then the number of degrees of freedom will be number of groups minus 1. So in our case 2. Let's check it. So this is the, you remember when we make a chi-square test, it's always right tail test, because the larger chi-square, the more extreme the value is. So therefore, we simply need to compute an area on the right side of this value. This is degrees of freedom. And then you can see this is our p-value. So again, if we work with significance level 0.05, we reject null hypothesis. So we can claim that we have a statistical evidence against null hypothesis. So at least one company produces tablets which are either longer, or work shorter, right? If you, for example, want to do it in R without all these manual calculations, you can just enter the data. So in this case, you can see I enter ABC directly. And then I will use the same approach as in ANOVA. So I produce vector Y with all these values. And then I use vector G, which contains these letters A for the first 10 values, letter B for the next 10 values, and then letter C for the last 10 values, right? So it's like 2 columns. And then I just simply use formula to compute Kruskal test. In this case, you can see that the outcome, both statistic and the p-value, they match what we got manually. So our calculations are correct. Okay. Like in ANOVA, Kruskal-Wallis test doesn't provide you details. It just tells you how significant the difference is. If you see a small p-value, it's an evidence that at least one group is different from the others, but it doesn't tell you which one is different. In ANOVA, you remember we apply Toki test to get the details. What you can do here? Well, first of all, you can do pairwise Mann-Whitney test, right? But remember to make a Bonferroni correction. It's not the best choice, but sometimes people do it anyway. There is an analog of Toki test for Kruskal-Wallis called Dunn test. So it's a post hoc test. It's kind of similar as you use Toki for ANOVA. It's also kind of ad hoc test. So it's something that you use based on the Kruskal-Wallis results. And that gives you also the idea of pairwise comparison. There is another choice. You can actually compute confidence intervals. For example, in this case, you can compute confidence interval for the median, because since we are talking about shift between distribution, median can be a good way to estimate the shift. But of course, it shouldn't be individual medians. It should be difference of median values. Like Toki's test or t-test for 2 samples computes your confidence interval for the difference of mean, you can compute difference of median values. But we know that it's not possible to compute confidence interval for the median values. It doesn't follow any distribution. Yes, but there is a function, there is a method for that. It's called bootstrap. And that's what we are going to watch in the next video. However, before we go to the next video, let me show you another similarity between Kruskal-Wallis test and ANOVA. If you remember, ANOVA is a generalization of t-test. If you apply ANOVA to the data set, which is specific for t-test, for example, 2 sample, right? You have 2 samples. The ANOVA p-value and t-test p-value will be identical. The same about Kruskal-Wallis and Mann-Whitney test. So Kruskal-Wallis is just a generalization of Mann-Whitney test. So let me show you that. You remember, this is the data set with only 2 set of tablets, which I used to show you how Mann-Whitney test works. So this is the Wilkes test results, right? So you can see this is the p-value, but I turn off the correction. That's important. And this is Kruskal-Wallis test results for this data. Look, the p-values are the same, right? So strictly speaking, Kruskal-Wallis test and Mann-Whitney test, Kruskal-Wallis test is more general way to make a Mann-Whitney test, which works for any number of groups. Like ANOVA is more general way to make a t-test. Okay. Now we complete all the 3 tests I planned you to show. Now let's talk about bootstrapping in the next video, and then I will also use the next video to conclude the whole learning sequence.